Okay, this is chapter 18 on global climate change in the Withgott book. So the case study at the start of the chapter is talking about sea level rise. The old case study in the previous book talked about an island nation called the Maldives and how they might completely disappear with sea level rise. But the new case study now is about Florida and how Florida is having to go to some extreme construction effects to just keep, parts of it from being completely underwater. Then we move on, section 18.1. It's called Our Dynamic Climate, and it's talking about climate change. And you should know the difference between the terms climate and weather. Climate is what happens over a long period of time. Weather is what's happening at the moment. And then there's some bold terms over here that you should know. But specifically, it's kind of talking about the greenhouse effect and greenhouse gases. So this picture over here, you should know this figure and caption. It shows incoming solar radiation, and it comes into the earth, it gets absorbed by the surface, and then any sort of body, like in physics we say a body, when it absorbs energy, it will re-radiate that energy back out, and usually it's at a different wavelength. And so this comes in as electromagnetic radiation, and it gets emitted out as infrared radiation, kind of like what we would consider as heat. A lot of it goes through the cloud layer, through the atmosphere, and just back out into space. But some of it gets trapped by the atmosphere, by the greenhouse gases in the atmosphere, and that's called the greenhouse effect. If we did not have the greenhouse effect, then we could not live on this planet because it would be far too cold. All the heat would get radiated back out into space, and people wouldn't be able to live here. So the greenhouse gases cause the greenhouse effect. And they are really good. They trap heat and they make the planet livable. So in general, greenhouse gases are kind of a good thing. But what's happening now is that we are having an overabundance of greenhouse gases. And so the greenhouse effect is kind of spiraling out of control. So you need to know what the greenhouse gases are. There's CO2, carbon dioxide. There's water vapor. Water vapor is naturally occurring. It is the one that there is the most of in the atmosphere, but it's really a cycle that humans don't affect very much at all. We might dam up a river and then the reservoir behind it might evaporate a little more or something like that. But for the most part, humans are not really having a huge effect on the water vapor in the atmosphere, which is good because, like I said, it's the one that there is the most of. Then there's CH4, which is called methane. That's a very powerful greenhouse gas. There used to not be a lot of it, but there's more of it now, which is kind of troubling. Then we have what's called nitrous oxide, N2O. And then there's CFCs and HFCs, which we talked about last chapter, chlorofluorocarbons and hydrofluorocarbons. So these greenhouse gases warm the troposphere. They absorb the outgoing infrared radiation that is reflected back, and so it's reflected back to Earth, like I was talking about in this picture over here. All right, and then we turn the page. And so CO2 is the one that they talk about. It is the most commonly talked about greenhouse gas. When people talk about carbon, they're really talking about CO2 and a little bit about methane. It is a naturally produced gas through cellular respiration, and for thousands of years, the amount on the planet was actually very stable. So this graph right here is kind of showing you the years since the year 0, right? We're in 2023 now. So this graph is showing you that for a long time, the levels were very stable. Carbon dioxide was stable, nitrous oxide, methane, very stable. And then the Industrial Revolution hit. And that's when we started burning fossil fuels, and the gases in the atmosphere just exponentially went up. So CO2 is the most abundant anthropogenically made greenhouse gas, and it comes from burning fossil fuels. You should also take a look at this chart, which is talking about which ones are worse. So it's basically their heat trapping equivalent, and then how long they stay in the atmosphere. And so methane is worse than carbon dioxide, but there's just not as much of it out there. Although more of it is coming because we are burning a lot more natural gas now. You should know some of the human activities that increase greenhouse gases. Number one is burning fossil fuels. Remember in chemistry, the combustion reaction, CO2 is a product. And so anytime you burn fossil fuels, you get CO2. Most of the time it goes up into the atmosphere. Raising livestock. Methane comes from cow flatulence. So when cows pass gas, it is there's a lot of methane in it. And that's actually a pretty significant source of methane in the atmosphere because there are far more cows in the US than there are people, and they're a lot bigger than we are. And not to mention the diet that we feed them in the concentrated feeding organizations is not their normal diet. It upsets their stomach and it makes them pass gas more. So livestock, methane from livestock is actually a pretty significant source of greenhouse gases. Landfills also produce methane. Methane comes from anaerobic processes. So inside a digestive system is anaerobic. Inside a landfill is anaerobic. Another one that comes from is growing rice. Rice is grown underwater. And so some of the vegetation that's underwater starts to rot, and then that produces anaerobic activity and you get methane gas. Same thing when new dams are built. When they make a new dam, they dam up the river and everything behind it gets flooded. They don't clear it out or anything. So there's trees and grass and plants and all kinds of things, and they all get covered by water, and over time they start to decompose and they produce methane because they're decomposing underwater and it's anaerobic. So kind of all of those go together in that respect. Then fertilizers have, nitrous in it. And deforestation and burning trees. So burning the trees produces CO2, and deforestation actually, the trees sequester carbon. When they take in the carbon, they make their biomass with it, and so they store a lot of carbon. So when we cut the trees down, that carbon goes back into the system. Okay, next page over here. There are some factors that actually do cool the atmosphere. And you should be aware of those. So one of the natural ones is volcanoes. So a volcano goes, a volcano erupts, a lot of soot and ash goes up into the atmosphere, and it can actually block the sunlight a little bit. So these things happen because the sunlight gets blocked and the atmosphere gets cooled down. This does happen a tiny bit from fossil fuel burning because of smoke, but the CO2 effects are far greater than the cooling effects that happen because of the smoke that comes from burning things. And then also sulfate aerosols, which are small sulfate particles that float in the atmosphere and can block sunlight and cool the atmosphere. So there are some things that can cool the atmosphere, and that will come into play later in the chapter. Page 490, it talks about how climate varies naturally, and there is a section here about the Milankovitch cycles. This was a Serbian mathematician in the 1920s who discovered that different things about the Earth changed over periods of thousands of years. The orbit changed, the axial tilt changes, and the wobble, it's hard to describe precession, but you have an Edpuzzle about it. And all three of those things can actually cause ice ages or tropical periods, like when the dinosaurs were around and things like that. So he discovered those. You should know what they are. And then we get over here, and it's talking about how the ocean's thermohaline circulation has a lot to do with the climate. If the ocean were to become slightly warmer for whatever reason, the currents that move in the ocean are going to carry that heat to other parts of the planet. So all of this thermohaline circulation is kind of what moderates the temperature, but if it were to get out of whack, it could be disrupted by global warming. The Gulf Stream is the warm current that goes along the East Coast and then goes over to Europe, carries a lot of heat with it. If the Gulf Stream were to be disrupted because of climate change, parts of Northern Europe might become unlivable. Okay. Then we get into the second section, which is about studying climate change. And this is basically like, what are the things that we've used to learn what we know? How do we know what we know? One of the main pieces of evidence is there was a guy, I don't remember his name, I think it was like Charles Keeling or something like that. And he realized that we just didn't know how much CO2 there was in the atmosphere, even though people had an idea that, they had an idea that CO2 was warming the atmosphere in the late 1800s. And he realized that we didn't have any information. So he went to Hawaii, and he set up an observatory on the island of near Mauna Loa. And so this right here is called the Mauna Loa graph, or the Keeling curve, because he developed it. And so he picked this location because it was away from continents. So it was kind of out in the middle of the ocean. And continents have a lot of vegetation on them. And so that vegetation can hold heat, or there's a lot going on there. And so it's away from that. And he actually also put it on the rim of a dormant volcano. So it's basically on a slab of bare rock in the middle of the ocean. So, and he did all that so that the results would not be skewed by factors like vegetation. So this started measuring the CO2 in the atmosphere in 1958. And so they've been continuously measuring it since 1958. And this is the curve that has happened since then. So you need to understand a couple things about this curve. You can see that it zigzags up and down. The blue line zigzags up and down. And then this red line kind of shows you the line of best fit. So the bottom of the zigzag pattern shows summer in the northern hemisphere. And so you always need to remember the northern hemisphere has the most land mass and trees. And so when it's summer and the trees have leaves, they're going to remove all this CO2 through photosynthesis. So the level of photosynthesis in the atmosphere is actually going to drop in summer in the northern hemisphere. And then the top of the pattern is winter in the northern hemisphere. The leaves fall off the trees, there's less photosynthesis, and there's more CO2 in the atmosphere. And so it's basically like this yearly breathing cycle of the earth, right? Like it's taking in CO2 and then it's not taking in CO2. And so like if ideally it would just go up and down in a straight line, but it's been going up and down, and the ups have been getting higher and the lows have been getting higher than the previous lows. And so the trend line has been up since 1958. Okay. And then it talks about ice core sampling. And starting on this page, it actually does talk about proxy indicators. We weren't around hundreds or thousands of years ago, or hundreds of thousands of years ago, to measure, the climate at the time. So we need to use we need clues to tell us what the climate was like at that time. So some of the proxy indicators of climate change you should know about are ice cores. And this page, actually underneath my sticky notes, has a really good section on ice cores. So what they've done is over time, it snows in the Arctic and the Antarctic, and that compacts and it forms ice, and then it just keeps going. And so this layer of ice has been growing for thousands and thousands of years. And so they drill down and they take a core sample of these ice samples over mostly in the Antarctic. And inside, there are trapped bubbles of gas. So when it snows and it compacts, it gets little bubbles of gas inside it. And that bubble of gas actually shows you what the atmospheric condition was at the time that gas was trapped inside the ice. And so they can go back in time and look at what the atmosphere is like through these little air bubbles that are in the ice cores. Another thing that they use are sediment beds. So sediment beds are like at the bottom of a lake or a river or something, or sometimes it could even be in a dry area. But there's a lot of sediment built up, and things like pollen grains and plant remnants will be buried inside the sediment, and you can tell what type of plant was growing. So if you were like in northern Canada and you found pollen and plant remnants from a tropical plant, you would say, well, at some point in the past, this was a tropical region because this tropical plant was growing here. Another proxy indicator are tree rings. Tree rings can reveal dry and wet years and fire history. And so, trees, the oldest trees are maybe a couple thousand years old, so we can only go back a few thousand years with those, but it's still helpful information. This one's a little bit out there, but it's kind of interesting. an animal called a pack rat. They like store stuff. And the area that they store stuff in, you think it'd be called their nest, but it's actually called a midden. And so pack rat middens, they can find these in caves or things like that, and they're preserved pretty well. And they preserve seeds for hundreds of years because the rats have stored those. And so they can find, based on like what layer and things like that, you find a tropical seed in a cold area, then you know that that was once tropical and so on, kind of like the sediment beds. And then finally, coral reefs are another place that we can use to look at climate change indicators. They take in trace elements and isotopes. And so the ratios of these, they grow very, very slowly. So if you see a large coral, it's probably been growing for decades or centuries. And so if you look at the lower part of it and you look at what it's made out of, you can tell what was in the water. You can tell the water chemistry at the time that coral was taking in chemicals to build its skeleton. So those are proxy indicators of climate change. Then this is talking about models. It's pretty interesting. It goes into some of the computer modeling and things like that we are doing to predict the future and what's going to happen with climate change. Then we get into the bigger sections of Section 18, impacts of climate change. This starts talking about the Intergovernmental Panel on Climate Change, which is often called the IPCC. You should know what the IPCC is and what it does. They meet every couple of years, and they look at the current research that's going on, and they make recommendations to governments. And so these are intergovernmental. This is an international group, governments from all over the world. You should know these charts. This is talking about how this is showing you average temperatures over time. So in the 1880s, we did have a cool period, and a lot of that had to do with the soot and things like that from the Industrial Revolution blocking sunlight. But then once they started cleaning that up and all the CO2 got into the atmosphere, then you can see that we have been having warmer than average years since the early 1900s. So you should know about the temperature change that's been going on over time. You should know this figure and caption. This shows temperatures across the United States and the change that's occurred. Some small areas have gotten cooler, but for the vast majority of places, they have gotten warmer, and some of them have gotten significantly warmer. This is a 1.5 degree Fahrenheit temperature change since 1901. And so that's pretty significant. That's almost a full degree Celsius. And then it's talking about changing precipitation levels. Extreme weather is basically the new normal. So we can't look at what's been happening in the past. We are just crazy things are going to happen, stronger hurricanes and all that kind of stuff. And then this is getting into, that's just kind of a science behind the story. You should look at it because it does talk about changes to the jet stream and this polar vortex that people have been talking about in the news a lot lately. But then we get into, some of the other impacts. You should know this figure and caption on glaciers. So we know a lot about what's been happening to glaciers because people have been taking pictures of them for a long time. So these two pictures are Jackson Glacier in 1911 and in 2009. So not even 100 years. And you can see that this entire portion of the glacier is gone. And it's melted away because of rising temperatures. And then it talks about some other things like floods after major hurricanes and things like that. So why should we care, about melting glaciers? Well, melting glaciers actually creates a positive feedback loop because the ice decreases something called albedo, A-L-B-E-D-O. You should know that term. It means how sunlight reflects off of a surface. So if it's ice and it's mostly white, the sunlight will just reflect off of it and mostly go back out into outer space. And so it won't cause any warming. But if it's land, which is like green or brown, then the sunlight will hit it and it will absorb into it, and then it will be re-radiated back out at a lower wavelength and get trapped by the greenhouse gases. So less albedo means more heat absorbed, and more heat absorbed means more ice melting, which means less albedo, which means more heat absorbed, more temperature increase. So it's a positive feedback loop because it keeps getting worse and worse. Another effect is melting permafrost in the tundra. Permafrost is ground that is permanently frozen, but recently it has been melting and it's releasing a lot of trapped methane that exists in the peaty material inside the permafrost. And this is also a positive feedback loop because the more methane that gets released, the more it warms and the more the permafrost defrosts. Sea level rise is another major impact of global warming. What you should really understand about sea level rise, a lot of people think it's because of the melting of the glaciers of the ice, and that's true, but that's actually the second most important reason. The number one reason that sea levels are going to rise is because of thermal expansion of water. When water gets warm, it expands, just like anything does. And so as it gets warmer, it's actually expanding more, and that's the number one reason that the sea levels are rising, and not like the melting of the glaciers and the ice. You should know, this curve, which is kind of basically saying the same thing, it's showing you the causes of sea level rise. And it says thermal expansion is the largest at 39%. Glacier melting is at 27%. And then the ice sheets are at 21%. And groundwater extraction is actually causing sea level rise because that water has been underground for thousands of years. We're pulling it out, we're irrigating our crops with it, and it's going back into the water cycle, going up into the clouds, raining down, and that also has an impact on sea levels. So sea level rise can be majorly catastrophic for countries like the Maldives and Indonesia and places like that are island nations. Most of the people there live less than 1 meter above sea level. And so if the ocean were to rise a meter, that entire country would disappear. This has all kinds of effects, not just, environmental, but economic and political, because those people would then become refugees. Their country would be literally gone. And so other countries would have to take them in. And so it's more than just an environmental disaster. Another impact that you should know is about ocean acidification. Lots of impacts. So ocean acidification, we've talked about a little bit in the past when we were looking at the ocean. But basically, the more CO2 there is in the atmosphere, the more CO2 dissolves in the ocean. The more CO2 dissolves in the ocean, that makes carbonic acid, which lowers the pH of the ocean and has a lot of catastrophic effects on marine life. Animal populations are shifting, so because of climate change, some of them are moving north. So things like Burmese pythons that are invasive in Florida, as it gets warmer and warmer, they will make their way north. And I've actually seen a study that said they could get as far north as North Carolina or further. Alligators, like we used to think, oh, that's just a Florida thing, right? Well, alligators are in South Carolina now. They've come north through Georgia and into South Carolina. And if it gets warm enough, they may come into North Carolina. Additionally, some animal populations are shifting their altitude. So if they lived kind of near the base of a mountain and it's getting warmer, they're going to go up the mountain to try to continue maybe the colder temperatures that they're seeking. So a lot of animal populations are shifting, and then plant populations can't move. So some of them are struggling or dying out because of climate change. This is talking about farms and forests experiencing a mix of impact. Plants act as a sink for carbon. Remember, a sink means that it takes it in because they turn the CO2 into biomass. So in photosynthesis, they take in the CO2 and they actually, they use it to make energy, but they also use it to make plant tissue. They turn it into biomass. It gets sequestered inside them. So in the short term, more CO2 means that forests may become more productive because there's more carbon for photosynthesis, but this is only in young forests. In older forests, they actually aren't setting as much biomass as young forests are. They're not growing as fast, and so they're not going to be taking in more carbon. So In the short term, it's kind of a benefit for a young forest, but in the long term, more CO2 in the atmosphere is just bad. All right, and then it talks over here about health, wealth, national security, economy, all of these sorts of things. You should read this page pretty carefully and know 2 to 3 effects of each of them. So health, in terms of air pollution, hotter temperatures, it makes people sick. They have respiratory issues. There's an expansion of tropical diseases. So mosquitoes, if it gets cold in the winter, that can cause a die-off in mosquitoes, and that's actually really good for keeping their populations down. But if it doesn't get cold enough in the winter to kill them off, then the populations will get larger, and that will lead to a spread of, mosquito vector diseases such as malaria, and the new one like Zika and things like that. And then people can, get injured from storms, hurricanes, things like that. There are social and economic costs to things, like I was talking about in terms of refugees, rebuilding after a large hurricane or things like that. Agriculture and forestry have massive impacts from climate change. And then in terms of national security, I don't think it's out of the question that wars will be fought over things like water and agricultural land and things like that. And there are refugee issues to think about. So you should know some of the, these big effects too that are not just environmental. And then it talks about in the United States, and these are some of the predicted impacts of climate change in the United States. There's a whole bunch of them. You should know a few. If an FRQ were to ask you something, you should know some of them, like extreme weather events will become more frequent, or health problems due to heat will increase. So pick a few of those and memorize them. Then we get to the last section, which is about responding to climate change. So kind of like, what can we do? Hopefully it's not all doom and gloom. So what can we do? You should know these terms: mitigation, adaptation. So mitigation means like basically trying to lessen the effects, but knowing that the effects are going to come, or maybe lessen the effects and keep temperature rise down or something like that. Adaptation is kind of this idea that, well, climate change is going to happen, and so we need to adapt to it. We need to build larger seawalls, or we need to move our developments away from the coast or things like that. Energy Star, that's like a term that's used for appliances, and it means that they are energy efficient. And then you should always keep this idea that you vote with your wallet. Everything that you do, every product that you buy is endorsing some behavior. If you buy sustainably raised things, then people who farm sustainably will make more money, and people will say, hey, this is a viable way to make a living. Versus if you buy cheap, factory-made, fast fashion kind of stuff, then you are endorsing that way of living. You should think about these things over here. So this is talking about how you get around, and they always say walk or bike. I know that that's not necessarily really reasonable in Charlotte, but maybe you could bike somewhere close by. You should think about how you get your power. You should think about using energy-saving products. You should think about what you eat. The less beef and pork you eat, the better that is, because if you remember when we talked about agriculture, they use tons of resources, and they actually are, producing methane and things like that. What you do, you can be an activist. You can write letters to your congressman. You can work for a nonprofit that is interested in these sorts of, being an engine for change and things like that. And so there's more kind of in here. This is more pictures with captions, and then these are more like what you can do in terms of bulleted list or whatever. And then this graphic right here on page 512 is pretty important. How can we stop global warming? Well, it's probably not a one-page synopsis, but there's a lot of really good stuff on here. Modernizing the electric grid, improving batteries, retrofitting buildings for energy efficiency, all of these sorts of things. expand wind. So read this page, think about some of the things that are on here, because we can stop and reverse it, but it will take a concerted effort by literally pretty much every person on the planet. And then over here we get into what role should government play? And some people would say none, and some people would say everything. And the answer is probably somewhere in between. But this talks about how governments have passed laws, and then some people have used executive action to try to address climate change. Then it gets into the economics, government economics, really about carbon, that we can put a price on it. So you should know what carbon pricing is. You should know what a carbon tax is. And that's basically a tax on the carbon content of fossil fuels. So if you use a lot of fossil fuels in your industry, then you will be taxed for that. Fee and dividend is basically you charged a fee if you use a lot of fossil fuels, but then you can claim that on your taxes and the government will pay you back for it. And so it's a way of sort of like subsidizing it and getting it, making people attempt to use less. Carbon neutrality is this idea of, it's kind of wishy-washy. Some people say stuff, carbon offsets is kind of the similar thing. Like, if you buy a plane ticket and then you buy some carbon offsets, then this company will go plant a bunch of trees, and those trees will offset the carbon that you used for your plane trip. Well, yeah, maybe in 50 years, but they're not going to do it right now because they're planting baby trees. So there needs to be a little bit more than just this sort of feel good, I'm going to plant a tree and offset the carbon that I use. Then we're getting kind of towards the end here. You should know carbon capture, carbon sequestration, carbon storage, and cap and trade. All of these things have to do with ways of the market regulating carbon. Carbon capture obviously is just keeping it from going out, like things on smokestacks or things like that. Sequestration and storage are very similar. They have to do with like putting it somewhere. Some people talk about injecting it into bedrock or down underground. And then cap and trade is saying that I'm going to put a limit on how much an industry can emit. And if you want more, then you're going to have to buy carbon credits from some other company. And then it's talking about the Kyoto Protocol, which was in 1997. And the U.S. said that they were going to try to eliminate 1/5 of their emissions. We have failed. But we didn't sign on to the Kyoto Protocol originally because developing countries like China and India were not forced to the same strict standards that developed countries were. They still were allowed to emit and burn coal. And so the U.S. said, well, if everybody's not going to do it, we're not going to do it. And so we did not sign on to the Kyoto Protocol at first, but you should read about what that was. And this diagram is, again, going back to cap and trade and talking about, so like if you have these companies and they're both polluting a good bit, and then this one says, well, I'm doing whatever to lower my emissions. And so they're below their cap that they're allowed to emit. This company can pay them money and they can give them allowances so that this extra carbon dioxide that they're emitting is kind of accounted for in their cap. It's a little bit of a smoke and mirrors kind of situation. Then it gets into the Paris Agreement, which was in 2015, and the U.S. did sign on to this one, and most of the nations in the world actually signed on to it. And so everybody was like, oh, we're going to limit our emissions and we're going to halt temperature increases and we're going to keep it from going above, 1.5 degrees Celsius. And we're already probably past the point for that to happen. But there has been some success. A lot of countries, there's been massive buy-in. People, got people talking, and it has moved the needle in terms of governments and climate change. But it hasn't been enough to halt the temperature increase. And so we are still, if you look at this graph, it's sort of saying the Paris Agreement goals would be right here at 1.5 degrees. And we're probably not going to get there. Probably going to be a little more than that. And then this last little bit, I was talking about how some things cool the environment. You should know about geoengineering. Geoengineering is the idea, it's kind of a last-ditch effort, but it's something that some people have brought up as an idea to reverse global warming, where maybe you would put on purpose things up into the atmosphere to lower the solar radiation that gets through to the planet. I personally think that sounds like there could be a lot of unintended consequences that come from that, but you should definitely read this section about geoengineering and see what you think. All right, that's chapter 18.